back. So here's number 8. And again, these are review questions, not connected to 5.1. So the graph of the derivative is shown, and you have to use that to sketch the second derivative and f. So for this one, I'm going to draw a number line. I know these are tricky, so we got to practice them. We got to do a number line for the derivative, and I'm looking at where the derivative, in this case, for the first derivative, where it's equal to 0, or if there's any holes or breaks. So at 0, and it goes from 0 to 6, so I got to make sure it goes 0 to 6. 0 is a critical number, and positive 3 is a critical number because they make the derivative equal to 0. So I'm looking for x-intercepts. That's 0 and 3. And then between 0 and 3, it is above. So it's positive. Between 3 and 6, it's negative because it's below. I'm going to do a second derivative number line. Let me show you what I've done so far. So I've done a first derivative number line. From 0 to 3 is positive. From 3 to 6 is negative. And again, I'm going to go 0 to 6. Now what I'm looking at is turning points, or where it increases and decreases. So where is it increasing? So from 0 to 2, it's increasing. And then from 2 to 6, it is decreasing. And at 2, it's undefined. Now, from 0 to 2, it's just a line, and the slope of that line goes up 1 and over 2. So it's 1/2. All right, let's graph this. So from 0 to 2, it's increasing, and the slope is 1/2. That means the graph of this will be a constant at 1/2. And then from 2 to 6, it's decreasing. All right, so this will be the graph of the second derivative. I'll do that first. So find where 1/2 is. And at 2, it's undefined. So it either can be a hole or an asymptote, however you want to see it. So right here at 1/2 and 2, So between 0 and 2, and this is going to be a hole right here because of the sharp corner or cusp. It's 1/2 all the way through. And then what happens is that it's going to go below from 2 to 6. It's below. So we're going to do a little asymptote too here and show that it's below, and you have a graph. Oh, and it goes to 6, right? So wherever 6 might be, 3, 4, 5, 6, let's say it's here. So that you show a second derivative, that there's a constant for the derivative, and then a curve that's negative. And if we have a situation where it's undefined, you could also create a hole in that situation. So you see it's undefined. But an asymptote works as well. And there you go. How about for the graph of the actual function? What am I looking at? So for the function, it says start with the point, what did they say? 2, 2? 0, 2. So start with 0, 2. So I'm going to start with 0, 2. Here's 0, 2. And then I just need to follow this. So it goes from 0 to 6. 1, 2, 3, 4, 5, 6. So from 0 to 3, it is increasing with a smile. In fact, to 2, it's increasing with a smile. So we're going to increase with a smile. And then at 2, it continues to increase. But now it's going to increase with a frown. So it increases to 2, and then it's going to continue to increase, but with a frown up to 3. At 3, it's no longer increasing, but now it's decreasing, and it frowns all the way to 6. So let's just take it one part at a time. from 0 to 2 it smiles, from 2 to 6 it frowns, from 0 to 3 it increases, and then from 3 to 6 it decreases. And at 3 there should be a maximum. So you have the function, you have the second derivative, all based on the first derivative. Number 9. In number 9, it says the volume formula for a cone is 1/3 pi r squared h. It says the derivative of the radius with respect to time is 3, and it's 3 inches per minute. Positive means the radius is increasing. And it tells you height is equal to 3 times the radius, and then our goal is to find dv by dt when r is 6. So I'm just writing down all the information. So the formula, the information I'm given, and now let's do it. So I have too many variables. So before I go any further, take out h and put in 3r. So I have one variable on the right. Then simplify it. 1/3 times 3 is 1. And r squared times r is r cubed. So all of it together is pi r cubed. Take the derivative with respect to time. So that's with respect to time. 3 times pi, subtract 1 to the exponent, but it needs a hook. Dr by dt. And then substitute it. So r is 6. The rate is 3, and then put it all together. So if I multiply this together, I get 324 pi. And because it's volume, it's inches cubed. And because it's rate, it's inches cubed per minute. And that's it. And then write a good sentence. When the radius is 6 inches, the volume is increasing at a rate of 324 pi inches cubed per minute. So you have a great sentence that includes what was given in the question, and you answered it. Number 10. Number 10, you have an airplane. And it says it's flying at an altitude or height of 3 miles. When the plane is 5 miles away from the station, the radar shows the distance s is changing at a rate of 300 miles per hour. What is the plane's speed? So we have a rectangle. I'm going to draw it. So when the plane is 5 miles away from the station, I want to make sure that's S. So S is 5 miles. It says the rate of S with respect to time is 300 miles per hour. That's a rate. And my goal is, what's the plane speed? So in this case, that's dx by dt. So I can't even pretend I'm going to draw, well, I'm going to do it anyways. I can't draw an airplane, but that would be the airplane. X is how fast the plane is going. And this is the information given. This is the plane speed. dx by dt. So I need to have an equation that puts all of this together. And if it's a constant, it can be just a number. But if it's changing over time, it is. So 3 is a constant. It's just flying at that one level height. But x and s are changing over time. And here's the station. So in other words, 3 squared plus x squared equals s squared. If it's a constant, it goes in right away. And if it's changing over time, it needs to be a variable. This is 9 oh, it doesn't matter. Take the derivative with respect to time. So that's 0. So that's 2x dx by dt. 2s ds by dt. That's the derivative with respect to time. I don't know what x is, but I can solve it. So when s is 5, what's s? So s is 5, what's x? So like 3 squared plus x squared equals 5 squared. What does x equal? That's a 3, 4, 5 triangle. Or you can solve it to see it's 4. So I'm going to plug in 4. The rate for x is what I'm looking for. That's my goal. S is 5. And the rate for s is 300. Now I need to get dx by dt by itself. So I got 2 times 5 times 300 divided by 2 times 4. So the 2's divide out. 4 goes into here evenly, I think 75 times. I know it's 75. And then 5 times 75 is 375. And then write a good sentence. Is 375 miles per hour when the plane is 300 or 5 miles away from the station. So at the moment the plane is 5 miles away from the station, the plane's speed is 375 miles per hour. Number 11. In number 11, it says use the graph. Let's go down here. Use the graph to answer. Wow, a lot of questions, but this is it. So this is the end of the assignment. So let's just go. Let's do this. These are actually fairly quick questions, I hope. What's the limit as x approaches 0? So if you look at 0, I'll use my little arrow. Look at 0. Notice the left and the right do not agree. The limit does not exist. B. Find the limit from the right. So what's the y value it's approaching from the right? It's 2. Don't be scared of the hole. Not what it is when it gets there, but what it's approaching. It's approaching 2. That's the answer. From the left, nope, C is what's the limit as x approaches 4? So at 4, both sides approach the same thing. So you can say infinity, or you can say it does not exist. D. What's the limit as x approaches infinity? That's the right end behavior. So where's the right end behavior going? To the asymptote, which is at 1. So the answer is 1. E. What's the limit as x approaches 3? So here's 3. So from the right and the left, it agrees the y value is 1. F. At F, it says, where are the discontinuities? So where is there jumps, holes, breaks? So at x equals 0, where else is there discontinuity? At 4 and at 5. So 4 is an asymptote, 5 is a hole. So 0, 4, and 5. G, Willikers. G, which of these discontinuities are removable? So it's removable if the limit still exists. So 0 is not removable. The limit doesn't exist. Technically, at an asymptote, infinity means it does not exist, technically. So the only place that's removable is at that hole, because the limit still exists because the y value is approaching the same number from both sides. So the only one that's removable is at x equals 5. That's because the limit exists at 5. H. Find the absolute maximum from -2 to 3. So from -2 to 3, what's the greatest y coordinate? And that's 4. Find the absolute minimum from -2 to 3. What's the lowest y value? That's 0. J. What's the derivative at 1? Now remember, derivative means slope. So at positive 1, what's the slope that it's in the middle of? So you go down 1 and to the right 1, it's negative 1. So the derivative for j is negative 1 because it's the slope where it's a part of. What's the second derivative at 1? So if you take the derivative of that, you get negative 1, and the derivative of negative 1 is 0. Any constant would be 0. L, yes, I'm going to show you my page in a moment. L, where are all the x values where the derivative doesn't exist? So the derivative doesn't exist where it is, there's a discontinuity or a sharp turn or corner. So at 0, it does not exist. At 2, it does not exist because the left and the right don't agree, kind of like an absolute value corner there. At 4, it does not exist because of the asymptote, and at 5, it does not exist because of the hole. So 0, 2, 4, and 5. M, and again, I will show you my page in a second. M, what are all the x values where you have a local minimum, the lowest point in its area? So at 0 is a low point in its area. Even though there's a hole and a jump, it's still a low point, a low value in its area. So when x equals 0, whereas another low point in there is that when x equals 2. So at 0 and 2 are the low points of the graph for x values. And then the last question, list all the values where there's a local maximum. So that does not include the ends. So negative 2 can't count. So if I look at any high points in the graph, I see a hole, I see infinity, and that's it in terms of a high point in the graph. So therefore, there are no local maximums. So when I look at the hole, it cannot be a maximum. Then I look at the going to infinity cannot be a maximum value. And that's it. That's the only high point. Right here would be a high point, but it's an end of the interval, so it does not count. It needs to be in the middle to be relative or local. And that's it. I promised you. Here it is. So those are all my values, A to N. And there's your homework. Mr. G Math, over and out. Until next time.